3.3 The second approximation. The second approximation of diode still treat diode as a switch and also include a diode voltage, which is the knee voltage. The equivalent circuit of the second approximation of a silicon diode is shown in the figure here. We use the same schematic symbol for second approximation. And then for the forward bias, which means when the diode conduct current, it's like a closed switch, so the current can flow through it. However, that requires a 0.7 volt on the diode in order for the diodes to run, in order for the diode to conduct current. In the reverse bias, it's a little bit different. It's an open switch because there's no current can go through it. The diode still holds that 0.7 volts. The current and the voltage curve for diode for second approximation is a little bit different from first approximation. As you can see, there's no current being conducted if the voltage is below the knee voltage, 0.7 volt. If the voltage is higher enough and when it reaches 2.7 volt, it starts to conduct. For the second approximation, there is no limit about how much current can flow through it. Therefore, it's a vertical line pointing to the top. Let's summarize the second approximation of the diode. The second approximation of diode treats diode as a switch with 0.7 volt knee voltage involved. The symbol is same, it's a regular diode. Just by looking at the symbol alone, we don't know it's first, second, or even third approximation. For second approximation, if the diode is in the forward bias, it looks like a switch with a 0.7 volt voltage source. And then in reverse bias, it's like an open switch connects to that 0.7 volt source. The diode curve is a curve. It's only activated when voltage reaches 2.7 volt. Otherwise, there is no current in the circuit, in the diode. When the diode is activated, in theory, infinite amount of current can go through it. The second approximation is mainly used for all type of calculations. Unless we need a more accurate result, that's the time we need to use the third approximation. Let's work on example 3-5 to reinforce the learning, to see how to apply second approximation to get the voltage, current, and the power. The question is to use the second approximation to calculate the load voltage, load current, and the diode power in figure. First, we know this is the second approximation. The voltage required to activate the diode is 0.7 volt. And we know this diode is in the forward bias, so current can flow through it. The power source provides a 10 volts. Therefore, the voltage across the resistor RL equals to 10 volts. Remove the 0.7 volt dissipated on the diode. The leftover voltage, 9.3 volt, is the voltage dropped on RL. To find the current that goes through RL, we use VL over RL, which is the 9.3 volt divided by 1 kilo ohm. That equals to 9.3 milliamps. Now we know the current that goes through the load resistor RL is 9.3 milliamps. Because the diode and the resistors are in series, the diode also has the same current. In other words, 9.3 milliamps goes through the diode. The ID, the diode current, is also 9.3 milliamps. To find the diode power, use the power formula. So the diode power PD equals to the voltage of the diode, which is 0.7 volt, multiply the diode on the current, that 9.3 milliamps. And after computing that, equals to 6.51 milliwatts.